Hello folks, welcome back to part 2 of our machine learning versus conventional modelling. I'm David Kearns. It's another With a Sharpie video. If you haven't already watched part 1 of this video, I recommend you go back. I've put a link to the first part of the video in the comment on this video that I've uploaded. What I'm going to talk to you about today is, I talked to you previously about conventional modelling versus and how they make predictions to enable us to predict the way that real systems will work. And there's a lot of work and they can work very well. What I wanted to talk to you about today is an alternative approach, something known as machine learning. And so I'm not going to get into the nitty-gritty of how machine learning works. I'm going to talk about this in sort of higher level, more abstract terms. But let's get into it. So I mentioned before that we build our conventional models. I've represented that as a black box. Over here I'm actually going to represent our machine learning model, and what's inside that model is actually something known as a neural network. And there's lots and lots of different types of neural networks out there. A neural network is a mathematical or a series of mathematical equations essentially, which enable us to create relationships between inputs to our model and the predictions that it makes. So it's essentially a form of statistical curve fitting, but working at a much greater level than the sort of curve fitting that you might have come across doing things like linear regression and so on. Oddly enough, we do often call the outputs of these regression. And so what do we get from this model? Well, unlike the sort of models that we would use in conventional systems, we don't put any information in here about assumptions or fundamental laws or anything like that. All we put in is that it's a two-phase operation, and it's all based on real-world operating data. And so we get a model that produces one prediction, just one. So it could be predicting an energy consumption, it could be predicting a production rate, or something like that. And for every prediction that you want to make, you need to build another machine learning model. So if you want to predict 10 different things, you build 10 models. They might all use the same source of data, but you'd have to build 10 models. So what's used in these? So our first phase is what we call a training phase. So the term kind of gives it away, machine learning. There's an idea that machines learn, and they learn from data. And how do we get them to learn? We train them. So there is a training step. What we do is we take this operating data up here from our real system. We take that operating data, and this is operating data that's historic. It's not real time. And what we can do is go through a series where we have operating data which is historic, which includes some independent variables. So these are things about the plant that we can change. Some dependent variables, some things that are affected by the independent variables. And importantly, it also includes the parameter we want to predict. So that's all in that operating data. We feed that into our machine learning model's training phase. A series of mathematical operations go on in the training phase. I will not go into those, they're far too complex for this video. And what we end up with at the end is hopefully with enough operating data and good, good clean operating data that hasn't been corrupted, doesn't have bad data in it, we can end up with a machine learning model which gives us a very, very good prediction of the thing we want to predict as a function of various operating parameters that we can measure in our plant. And you say, well, okay, that's interesting, but so what? Well, one of the things that I'd like to point out to you is that once you've got that model, okay, we can then move from our training step, we can now go to our deployment step or our use step. Okay, so here's our machine learning model. So this has now been trained. And we can then say, okay, let's get some real operating data out of our plant, just the independent variables, not everything. So it might just be, what's the temperature on the day, what's the feed flow rate, doesn't really matter. And it can produce predictions. And again, each model produces just one prediction. Just like these models up here, these conventional models usually can produce lots of predictions of different things out of the one model. Here, they're one at a time. This trained model here can be very, very accurate, and so that's really the first advantage. Because it's essentially it's a pure empirical process here. There are no fundamental laws we're trying to meet with. There are no assumptions. It just takes pure operating data and produces predictions through a statistical process. We can get very, very good accuracy. And the nice thing is we can get accuracy not only of good, R squareds, but also of functional form. So not every relationship in real plants is linear, for example, and yet if you go and do multivariate linear regression, it assumes that each parameter has a linear relationship to the thing that you actually want to predict. The nice thing is that machine learning models based on neural networks can actually infer the shape of curves of relationships, as well as try and line up these R squareds to be nice and accurate. The second thing that they can have is that these models are fairly quick to develop. So rapid development. So these models up here, as I mentioned to you before, it's pretty quick if you're using modeling software to develop a conventional model, but getting one that has good predictions that lines up nicely with a real system, that's really hard, and that can take a long time. This data reconciliation process is no joke. It can take weeks or months of effort of skilled professionals just to get one model that works for one part of a system. Another advantage is that these machine learning models are quick to use. So what do I mean by that? Conventional models usually contain lots and lots of different equations, and they have to converge. So they actually have an iterative element to them, where they go round and round and round doing calculations. Every time you make a change in one little bit of operating data that goes into that model, you have to reconverge the whole model, and that can be quite slow. For simple systems, it might only be a matter of a minute or so. For really big complex systems like an entire oil processing facility, for example, that could take 15, 20 minutes, maybe up to a couple of hours to do rigorously. That's a long time. These machine learning models, they have a fairly significant computing and time requirement in the training phase, which we do up front. But once it's actually trained, the final outcome of this is essentially a matrix of numbers and can be used rapidly. And so this is the reason machine learning models, for example, are used in things like Siri or Cortana or any of the voice recognition systems that you might use on computing or phone devices. Those models have been trained extensively with huge data sets of people's voices, really big supercomputer type activities in this training step. But what you end up with at the end is something that can run rapidly on your phone in your pocket. So that's one of the nice things, is that we can actually split the computing load and do it all up front. I guess one of the key disadvantages of machine learning models, and it's just by the nature of it, is that machine learning models rely on data sets to be built. And if you want to do design, you can't do design with machine learning, at least not very easily. The reason for that is, well, if you've got building a model of a real system and the real system doesn't yet exist, you don't have the data. And so machine learning models are much better for systems that already exist and modeling systems. So I'll just say disadvantage is not for design. So there's still a place, an important place, for conventional modeling. It's not going away. So what can we do with these models? Well, there's a couple of things that I'd like to, I'll just move us up here now. One thing that we can do with our machine learning models is we can test new operating conditions. So we might want to say, well, what is our plant going to do if we bump up our flow rates, but we reduce our temperatures? Trial and error. And there's a few ways you can do that. You can do them one at a time by feeding new independent variable values into here. Or you can build them into a system that enables you to play with this as if it was a real plant. And so that's something known as a digital twin. So a digital twin is essentially a series of machine learning models to represent the performance of the plant. And then as you change the different independent variables that you're feeding into your model, you can actually see what would the plant do under different conditions. So digital twins are very, very good for reviewing historic performance of plant. They're also very good for training if you want to train plant operators on how your plant works, but you don't want to let them loose on the real plant up front. You can use a digital twin for that. Two, and for me more excitingly, they can be used for optimization. So what you can do is you can actually couple this machine learning model with, I'll draw it in a different color. You can couple this with a different mathematical routine, which is an optimization routine. And these two get coupled together mathematically. What an optimization routine can do, it can say, well, let's say the prediction here is energy use per ton of production. And let's say I want to maintain my level of production, but I want to minimize this energy use per ton of production. Well, what my optimization routine can do is it can say, well, okay, let's try lots and lots of different combinations of these independent variables, see what they do to this predicted energy use per production, and then using some mathematical techniques, figure out what values of independent values you could try that would minimize this energy use. And so one example is that there was an example by Google DeepMind about 18 months, 2 years ago, where they applied this sort of technique to optimize electricity use for one of their cooling systems in one of their data centers. And they dropped the electricity use by the cooling system by 40%. So this is no joke. This is not something fiddling at the edges. This is making double-digit improvements in the performance of a real-world system using machine learning. So I hope that gives you a little bit of an idea of some of the differences between how you might model systems with machine learning versus conventional modeling. There's still a place for conventional modeling, especially in design. But I think over time, because of these advantages of accuracy and rapid deployment, you'll see a lot more machine learning models being developed for things like digital twins and optimization and so on as we go forward. This has been David Kearns with another With a Sharpie video. Thanks for watching.